Kinematics requires you to be able to define displacement, speed, and velocity.
Welcome to Easy A Physics. My name is A Tove. I'll be covering kinematics today.
Distance traveled in a certain direction.
Now, the key point to kinematics is to understand how to draw your graphs. On the axis, there's distance, time of speed or acceleration. In this case, we're starting off with distance time graphs. So it's very important to include the unit as well on the y-axis as well as on the x-axis. Now, in the example shown here, we have an object that moved a distance of 50 meters in the first 10 seconds of its journey, and then maintained that distance for a further 20 seconds, which means that it was still 50 meters away from where it started. In this case, it means that the object was stationary for 20 seconds. The relationship between distance and time for this object shows that it's not a straight line relationship. The gradient of the line is changing. Now, on a distance time graph, the gradient is the speed. So it's shown in green there. The gradient is found by drawing a tangent at that point. So when t is equal to 10 seconds, you find the gradient of the tangent. That gives you the speed with which this object was moving. Now the gradient becomes steeper as time progresses. So as you can see, the speed of the object is increasing. Now the relationship between distance and time for this object shows that the gradient is decreasing. Remember, the gradient on a distance time graph is the speed. So it means this object is slowing down until it comes to rest. So when you have a flat line like this as shown in green, the speed is now 0, the object is at rest. Now on a speed time graph, the area under the graph is the total distance covered, and the gradient of that graph is the acceleration. Now you must always remember to label the axis with the quantity and the unit. So speed is measured in meters per second and time in seconds. Now on graph A, the gradient is constant, which means that the slope doesn't change. The slope represents the acceleration, so this is uniform acceleration. Graph B, this is uniform deceleration because the gradient doesn't change. Graph C, that is uniform speed. Please note the difference between uniform acceleration and uniform speed. Uniform speed means 0 acceleration. Graph D, this is non-uniform acceleration. Graph D shows that the gradient is decreasing, which means our acceleration is decreasing to 0.
The velocity of an object is its speed in a certain direction.
Now, the difference between the velocity time graph and speed time graph is that velocity being a vector quantity, you've got to show positive and negative direction in times. I have this example to show deriving a velocity time graph from a distance time graph. This is probably from an object that was thrown upwards and then reached maximum height and then fell down again. Now at the start, the gradient is shown by these tangents that have been drawn at particular time intervals. They show that the gradient was steep at first and then became less and less steep until we've got 0 gradient there, which means the velocity is 0. As shown on the velocity time graph, the velocity will be 0 at this position. When the object is launched, the object reaches a maximum height there. So at the maximum height, the speed is 0, as shown. So this is the positive part of the journey when it was moving upwards. Now when it reaches a maximum height, we've already said that the speed is 0. Now when it falls down, then the direction changes because the object is now moving in the opposite direction. It then occupies this quadrant, the negative quadrant, as shown there. When it is just about to hit the ground, it has reached again its maximum speed, so it ends up on a maximum but to be a negative value. Now we're going to look at the equations of uniformly accelerated motion. So we're going to start off by deriving them. We're going to use our graphical presentations to help us with this derivation. Now consider a body that starts off with an initial velocity u when t is equal to 0, and then moves with a constant acceleration. So remember from the graphs, the constant acceleration is shown by a straight line. Now u is the initial velocity, a is the acceleration, v is the final velocity after a time period of t. Equation 1 is derived from the gradient of the graph. We said that the gradient of a vt graph gives us the acceleration. So we're going to write acceleration is equal to the final speed v minus the initial speed u over the total time taken, which is t. Then if you multiply by t both sides, we have at is equal to v minus u. Rearranging the equation to get v on the left side of the equation, v will be equal to u plus at. So we're going to call this equation 1. Now equation number 2 concerns the average velocity. We know that when you're finding the average of two quantities, you've got to add them and then divide by 2. Now we add the initial velocity and the final velocity and then divide by 2 to get the average velocity. Then after that, we then try to find the total distance traveled from this average velocity. Now we know that total distance traveled, s, is equal to the average velocity times the time. So this is going to equal u plus v over 2 times the time, which is t. So this is our second equation. Now equation number 3 combines equations number 1 and 2. Remember from the first equation, v is equal to u plus at. The second one is s is equal to half bracket u plus v multiplied by the time. Now that's the format. S is equal to half bracket u plus v times the t. So v being equal to u plus at from equation 1. Now simplifying that gives us half ut, because this t multiplies that u, and then plus that bracket. Now we have ut plus at squared. Then we close the bracket. Remember this half multiplies everything, so it's going to give us half ut plus half ut plus half at squared, which then becomes ut plus half at squared. So that is our equation number 3. Equation number 3 can also be derived by looking at the area under the graph. Remember I said the area under a velocity time graph gives you the total distance traveled or the displacement. Now this area is divided into 2. We've got a rectangle and then we've got a triangle on top of it. So the total area is that of the rectangle and that of the triangle. So we then say S is equal to, the area of the rectangle is U times T plus the area of the triangle on top of it, which is half base times height. Half of the base is T multiplied by the height, which is V minus U in this case. So V minus U in brackets. Now from equation 1, we know that V is equal to U plus AT. So V minus U should equal AT. So we can substitute this into that equation. So then this gives us S is equal to UT plus half T times AT, which then gives us S is equal to UT plus half AT squared. So this is a simpler version of equation number 4 is derived by looking at again equations 1 and 2. This time we're substituting time into equation 1. So we're going to have from equation 2 with s is equal to half bracket u plus v times the time. So in place of the time, we're going to make t the subject in the first equation, which is going to give us v minus u over a. Having done that, we can now group the like terms together. So we have s is equal to 1 over 2a u plus v bracket v minus u. Now if you take 2a that side, it becomes 2as is equal to bracket u plus v bracket v minus u. Now this is a difference of 2 squares. So that's going to give us v squared minus u squared this side, and then 2as on the other side. Now making v squared the subject of the formula becomes v squared is equal to u squared, because it crosses the equal sign, it becomes a positive, then it adds on to the 2as. So this is our equation number 4. Now these are the 4 equations of uniformly accelerated motion. The first one, v is equal to u plus at. Second one, s is equal to half bracket u plus v times t. The third one, s is equal to ut plus half at squared. And the fourth one, v squared is equal to u squared plus 2as. Please take note that these equations only apply for motion in a straight line and also with uniform acceleration.